Okay, so all of that was from page 1. Okay, now jumping back down here, I want to add that on page 2, instead of the derivative, you're going to see omega written like that, delta omega over delta t. So we're going to stick with the derivative, okay? But what you see on the page, the delta theta over delta t, that doesn't change the analysis. And on page 3, okay, instead of seeing ds dt, you're going to see delta s over delta t. So we're going to stick with the derivative, okay, follow along with that. It doesn't change the analysis, but I just try to simplify something by just putting in delta s. All right. So remember in chapter 2, okay, so I'm trying to make the connection between the stuff we did in chapter 2, first week of February, and the stuff we're doing now. Okay. So in chapter 2, a person walks down the road, x was their position. Okay. When they changed their position, delta x was their displacement. Now we have something that goes around a circle. It could be a bicycle wheel, could be a person walking around a circular lake. Okay, so at any orientation around, we would say they have an angular position, right? 30 degrees, 90 degrees. Okay, we have to do it in radians, but that's their angular position. And as that changes, they have an angular displacement. Okay, well, just like in chapter 2, okay, if when the position changes during a certain period of time, okay, then they have a velocity. So the velocity v was defined as your displacement divided by your time. Okay, so just like the displacement can change over a period of time, okay, the car has a velocity, the angular displacement can change over a period of time. So here's your angular displacement changing over a period of time. So instead of calling it a velocity, that's called an angular velocity. Okay, so the v in chapter 2, that was velocity. Okay, this, okay, making the connection between displacement from chapter 2, displacement over time. Now it's angular displacement divided by the time. So that angular velocity, we use this letter omega. Okay, that's a small omega. That's a capital omega. Okay, so this is a small omega. So your angular velocity is the time rate of change of your angular position. Okay, it's your angular displacement divided by the time. Okay, and we're going to see, just like in chapter 2, that since velocity is a vector, we'll see that angular velocity is also a vector. Okay, the magnitude would be called the angular speed. Okay, all right. Now the units are kind of weird, right? So what are the units of theta? Radians, and time is always seconds. So the angular velocity omega has units of radians per second. All right, and we're going to remember that the radian is a dimensionless unit. Okay, we saw that earlier when the units of feet canceled out in our shoelace example. Okay, so let's say in this example, let's say I have your bicycle wheel. Okay, you take your bike off your tire. Okay, you're spinning it. Okay, and let's say this thing spins at 3 revolutions per second. Okay, so in these chapters, it could be a bicycle tire spinning. Okay, it could be a person walking around a track. Okay, let's say they make 3 revolutions per hour or something like that. So I have a wheel spinning at 3 revolutions per second. So remember we did the circular motion chapter. There were times where they gave you that something spun at 3 revolutions per second. And we said that that was the speed. And we said v was 3 revolutions per second. And we said, well, that's not really the correct units because v has to be in meters per second. And then we changed revolutions to meters by saying 1 revolution was 2 pi r meters. Okay, so that was kind of looking ahead to this. So this is called an angular speed. Okay, so this thing's going around 3 times per second. All right, so omega is your 3 revolutions per second, but it's not in the correct units. It has to be in radians per second. Okay, so in 1 revolution, I have 2 pi radians. Okay, and I'm not doing 2 pi r because it's not a distance. 1 revolution. Okay, so again, it's not 360 degrees. It's 2 pi radians. So the revolutions cancel, and I have 3 times 2 pi, so 6 pi radians per second. So that's my angular speed. Okay, now the direction of omega vector, that's the angular velocity. That's found using something called the right-hand rule. Okay, so the right-hand rule is, and I took these pictures from our book. So let's say this thing is rotating around, all right? Now, we're going to see why we don't want to call this, okay, clockwise or counterclockwise, okay? Because depending where you're standing, one person would say it's clockwise, one person would say counterclockwise. Okay, so here's the same disk, okay, rotating, all right? And to find the direction of the angular velocity, omega vector, okay, you grab the axle of rotation, okay, or the axis of rotation. Here, let's say the axle of the wheel. So you grab the axle or the axis with your right hand such that your fingers are curling in the direction of rotation, okay? So my fingers are curling in the direction of rotation. If that's the case, then your thumb points in the direction of omega vector, okay? So in this picture here, okay, this person didn't necessarily grab the axle, okay? They're just showing, imagine this is a lid, okay, of a jar, okay? So you're twisting the lid as a jar, okay? You're twisting the lid, all right? As you keep twisting the lid around like this, okay, yeah, the lid is twisting around, but after you keep twisting the lid, which way does the lid move? It moves up, okay? It moves up off of the jar. So that's how we think of the right-hand rule, okay? This one over here, okay, let's say, whoops, it's the same jar, okay? Now, okay, now this lid is rotating in that direction, okay? How do you find the direction of the angular velocity omega vector? Okay, same thing, right-hand rule. You grab the axle, okay, so imagine this is your axle, axis or axle. You grab that, okay? Right, now you can grab it either way, but when you grab it with your right hand, your fingers, okay, have to curl in the direction it's rotating, okay? And when you do that, your thumb points in the direction of omega vector, okay? So in this bottom picture, the angular velocity is down. So think of this, think of your thumb points in that direction, because here you're taking the lid, and if you twist it this way, okay, and again, this is the right hand rule, because most of the time, the things we use with threads on them, like a jar, those are called right-handed threads. So if you twist the jar lid like that, you're tightening the jar, okay, you're putting the lid on the jar. So as you twist it, which way does the lid move? Okay, lid moves down to tighten the jar. Okay, so that's the idea of the right-hand rule. Okay. Okay. So I'm trying to make the connection between the old stuff and the new stuff. All right. Now, let's say I have a bug and it's going in a circle. Okay. It can either be attached to a bicycle wheel, or the bug is just moving around the circle. Okay. Now, in the earlier chapter, we called that the velocity v. This chapter, they're going to call it the linear speed. Linear means along a line. Okay. Omega, okay, that's the angular speed. Okay. So a lot of times in this chapter, when we point at v, we'll call it the linear speed. Okay, so I want to find the linear speed of the bug. All right. So we know from the earlier chapter, okay, that linear speed, okay, whoops, wrong arrow. This one, that one, okay. That car goes down the road. Linear speed is displacement over time, delta x over time, okay. So here, okay, don't think of this as an x and y axis. The bug is moving along an arc. That's our arc length S that the trig books and geometry books like to use. So it's moving along that arc. Okay, so your linear speed is your displacement, not delta x, okay, because the road isn't straight, okay? The road is now bent in a circle. Okay, there's my arc. So it's my linear displacement S, that's an arc length S, divided by the time. But we already know, okay, that the arc length S is r theta. So right here I have an S, okay, there's an S. I put in, there's an S. I put in r theta. So my linear speed is the change in displacement, okay? The bug is moving along an arc, okay, so my displacement is S, and S is r theta. R is a constant, so it moves outside of the delta, so it's outside. And that quantity there, that's what we did on the previous page, that's your angular velocity, okay? So the old stuff in chapter 2 is related to the new stuff in our new chapter, there's our new chapter, okay, via the radius. So the linear speed of the bug, okay, linear speed as it moves around, it depends on the radius and the rotation speed, that angular speed, okay. Now the weird thing is what are the units of v? Well, in the old chapter is meters per second. Okay, let's see if anything changes. So if you want to calculate v, okay, r is a distance, so it has units of meters, so there's r, okay, some number in meters, and omega is the angular velocity, so it's some number in radians per second. So you take those two things, multiply them together, you get another number, and the units you have left are meters, okay, there's my meters, and there's my seconds. And you ask, what happened to the radian? Okay, well, in the old chapters, right, something moved at the speed was 7 meters per second, right? Didn't have a radian, so it's not going to have a radian now. So where'd the radian go? Remember, it's a dimensionless quantity, okay? It wouldn't be wrong to write it there, but it has no business being there, okay? So remember, that's one of the consequences of this concept of a radian being a dimensionless quantity. Okay, I want to discuss a little bit about why, for a rotating object, the direction of the angular velocity omega vector is chosen in the direction it is. Now, we had shown, I had a rotating object here. We talked about the right-hand rule, okay? So this object is rotating, We said you grab the axis of rotation such that your fingers curl in the direction it's rotating, your thumb points up, okay, and the direction of your thumb gives you the direction of the angular velocity omega. Okay, so I want to talk about why that is, okay, and why that decision is made. Okay, so here I have a rotating wheel. Okay, so this wheel will be rotating in that direction. So we might draw in the previous diagrams, we say, okay, it's rotating. So this little arrow shows that it's rotating. Looking at the screen, this would be counterclockwise. Okay, again, so we don't want to use clockwise and counterclockwise, because if you're on the other side of the wheel behind the screen, it'd be rotating clockwise. Okay, so this just shows that it's rotating. All right, and then here I drew a side view. Okay, so on both these pictures, I have some mass here. Let's say that's a chunk of the wheel. Okay, and each point of the wheel is moving in a different direction. So piece M1, okay, is headed in that direction. Number 2 is headed up. Number 3 is headed in its direction, right? So remember, these velocities are tangent, okay, 90 degrees to the radius, right? And so I just drew the exact same picture over here now as a side view. So this picture, this is the axis of rotation, okay? That would be in and out of the page. This, okay, this picture here, that's the axis of rotation, okay? So in this picture here, I drew the exact same masses, my M1, my M2, whoops, here's my M3, okay? And as the wheel rotates, okay, so as the wheel rotates with some angular speed, that's my angular speed, omega, each of these little masses is headed in a different direction. So mass number 1 has a velocity in that direction, okay, perpendicular to the direction it's going. Number 2 is headed in that direction. Number 3 is headed in that direction, okay? So each mass is traveling in a totally different direction, okay? So if I drew 50 masses on this wheel, they're all headed in different directions, okay? So what direction is common to every point, to every of those 50 masses on the rotating wheel, okay? Well, either up or down, meaning in a direction that's perpendicular. That symbol means perpendicular to the plane of rotation, okay? So the direction that's perpendicular to the plane of rotation, that's the axis of rotation. So I'm going to pick the direction of the angular velocity to be along the axis of rotation. Well, do I pick up or do I pick down? Okay, because the axis is a vertical line on this page, so either up or down. The choice to pick up or down is based on the right-hand rule, okay? And remember, the right-hand rule works for right-handed threads. So here you have a screw, okay, has right-handed threads. Here you have a light bulb that has right-handed threads. So if you grab the light bulb with your hand and you twist the light bulb, okay, as shown here. So think of the light bulb as twisting around with some angular speed omega, okay? So think of each little chunk of that light bulb moving like these little chunks of mass over here. So as the light bulb twists around as shown here, okay, which way does the light bulb eventually move? It moves up out of the socket. Okay, so you have the socket down here. Okay, so think of the right-hand rule working for right-handed threads. So that's what this picture is over here. I have little chunks of mass here. They're all headed in different directions. What direction is common to all of those? Okay, a direction that's perpendicular to the plane of rotation. So the axis is a vertical line. So to pick a direction perpendicular to the plane of rotation, we choose that based on the right-hand rule. Okay, so fingers curl around the axis of rotation, thumb points up in the direction of omega. So that's why omega is chosen to be up. It's based on the right-hand threadedness of the axis of rotation. And the other thing that we'll see about the right-hand rule is that if I take this light bulb, okay, and let's say it's screwed into a socket in the XY plane, let's say the XY plane is the table, okay, and if you take this hand to unscrew the light bulb, so I didn't draw the thumb, there's the thumb, okay, and the fingers go around like that, okay, so if you take your hand to twist the light bulb, just like it's being twisted here, okay, that the light bulb was rotating. Think about the light bulb rotating in the XY plane, okay, and the light bulb moves up in the Z direction, okay. So we'll also see when we get to the subject of torque that the XYZ, okay, that Cartesian coordinate system is a right-handed coordinate system. When you take something so like the x-axis and you start twisting it along the y, okay, that light bulb is going to move in the Z direction. Okay, so here I have a bicycle wheel, and I attached a bug at point A and a bug at point B, okay? And I want to compare the angular velocity of A. Well, forget about the direction. So I'll call these, well actually, what is the direction of the angular velocity of the bugs? Okay, well the bugs are rotating in this direction, okay? They're rotating that direction. So if something is rotating, and the way you're looking at the screen, you could call this counterclockwise, okay? So the axis points out of the paper, okay? Points out of the paper. If you took your fingers, there'd be your fingers would curl in that direction. Your thumb, there's your thumb, points outward toward us, okay? So actually, in this picture, omega is out of the page. So that's the direction of the angular velocity. Okay, let's not worry about that right now. Okay, so here I want to compare the angular speeds, omega for bug A and omega for bug B, and then I want to compare the linear speeds. Okay, well, remember the angular speed, okay, omega is my angular displacement over time. It's my change in theta, per time. Okay, well, my delta theta, okay, for bug A, when bug A goes around once, okay, delta theta is 2 pi radians. For bug B, it goes around once, it also goes around 2 pi radians, okay? So for each bug, the angular displacement is the same. And these two things are attached to a wheel. So each of these go around, if it takes 1 second for the wheel to go around, okay, then bug A took a second to go around, and bug B also took a second. So think of this as a bicycle wheel. Every point of the wheel took the same time to go around, okay? So every point on the wheel has the same angular speed. They're all rotating at the same number of revolutions per second, okay? Now, the linear speeds are different, okay? So the linear speed depends on how far you're out from the axis of rotation, from the center, okay? So bug A is close in, okay, so it has a small radius. Bug B is way out here. That's a far radius. Okay, so here's bug A, only has to go that distance. So I'll make that smaller. Here's bug A, only has to go that distance. Okay, and bug B is way out there. Okay, so in the same time it takes bug A to go from here to there. Bug B has to go the huge distance in the same time. So the speed of bug B, okay, is that huge radius times the same omega. Okay, so even though omega is the same for each bug, the radius isn't. Okay, so the farther you're out from the center, okay, the bigger your linear speed is. So if you get motion sickness and you get on a ride, okay, and you want to ask, do I want to sit close or do I want to sit far away? Okay, well, if you sit close, okay, let's say near the center, you only have to go a little bit of distance, that little distance, in the same time that this person would have to go that distance. So if you get motion sickness, okay, you would definitely feel it more out here than you would in there, okay? So the speed at B, the linear speed at B, is bigger than linear speed at A because the path length, meaning the distance to go around once, okay, in the same time, is a longer distance, right? Now, I claimed that you already knew that as a kid. If you ever rode your bike down a street and you put, let's say, a baseball card in the spokes, okay, there's the bicycle wheel, okay, whoops, okay, there's your spokes, okay. So you could put a bicycle wheel in your spokes to make a noise, okay. Now, where did you put the baseball card? Did you put it close at point A or close at point B? Okay. Well, the spokes are moving faster at point B, so you put the card out here so that the spokes hit it and make a much louder noise. Okay, now, this is part of the global consciousness and global awareness portion of the course, okay? So let's say you have an album, okay, and vinyl's making a big comeback with hipsters, probably because it's more difficult to copy, okay? So if you look at a record has a number on it, all right? It doesn't have the units. See, those units are really revolutions per minute, RPM, okay? So that number is omega. So it's 33 1/3 revolutions per minute, okay? So when you play a 12-inch vinyl record, the whole thing, or the whole record rotates the whole time, goes around 33 1/3 times each minute, okay? So that's omega, but it's not in the correct units. You'd have to say in one revolution, I have 2 pi radians, and then in 1 minute, I have 60 seconds, okay? So that would be the correct units of